Then continue. I think we are in 9.7. We are not totally done. We wrote down the solution for 1D, the 1D diffusion equation, and let's repeat it here first, and then we'll say just see how we generalize to 3D or 2D or 3D. Let's write down the equations. The equations for 1D is so your partial psi partial t. Right. Yeah. That's fine. Okay. A square plus a square psi plus x square. Right. That's 1D. And later on we want to go to 3D. 2D and 3D is just pretty much similar. But we talk about 3D in square. Now it's just change the Laplacian, right? And obviously, 3D will reduce to 1D if psi depends only on x, right? And now last time we wrote down the solution for the 1D problem. So subject to initial conditions. So initial condition is psi for 1D x t equals 0. Size 0. The given function is size of 0. X, right? And likewise, you can consider a 3D problem with x. Now it's a vector x at t equals 0. Size of 0 as function of vector x. Right. And now last time we wrote down the solution. This is also subject to the, we consider the infinite domain. At first we consider the finite domain also, but infinite domain, that's the boundary condition is at infinity, so there's some nice property of that. So basically we consider psi x goes to infinity, it's to 0, decay fast at infinity. Okay, and then that allow us to use Fourier transform, and now we wrote down the solution for psi xt now. And the 1D problem is just 2 pi and psi 0. Okay, this is the Fourier transform of the initial conditions. Okay, and then e to the minus. You have the decay, which depends on the diffusion coefficient and k squared t. And then you have the usual Fourier transform, phase factor I k dot x. Okay, actually, 1D problem just kx. Okay, right. And then we finally show that substitute the transform formula for the Fourier transform size of 0. We can show that psi xt also equals to, the textbook call it the alternate solution, but it's actually the same solution. Last time we showed that you can show it from here to here. So, it's basically still the same size 0 function, but x minus a factor, which is given in the textbook in the equation, the alternate solution, psi minus 2a square root of t, and then times c minus c squared d. Okay. 0 1D problem. All right, so that's how we did last time, right? And now the question is to generalize to 3D. Now what should it be? What should this correspondence to formula for that? Can you just write it down without doing all the derivation all over again. Can you just write it down? Like, look at these two and just write it down the solution. Can you do that? Do you think you can do that? Yeah. Do you know what I'm saying? So without doing the derivation again and just. Yeah, I change the audio to vector and make some corresponding changes in coefficients. Right. So, yeah, right. So psi for 3D would be like xt. Okay. Now instead of square root of 2 pi, you have 3D, right? 3D becomes 2 pi of 3/2, right? And then the integration will have will be over the 3-dimension k space. The Fourier transform of size of 0 depends on the wave vector k. Now it's a vector, right? And then this exponential factor would be the same with using the magnitude of k. Magnitude of the vector k would be just the scalar k, the magnitude k times t. And then the phase factor changed to the 3D phase vector ik dot x. And then integrating of 3D k space. Right? Okay. Can you accept this without doing the derivation again? Can you see why? Well, everyone can see why, right? Because it's when you substitute this Fourier transform, when you Fourier transform this equation, you pull a minus k square, right? The Laplacian of you take a Fourier transform of Laplacian, you pull a minus k square. So the equation of this is exactly the same as this one, except that this k is not just a single wave number; it's a magnitude of the wave vector. But the solution is the same. It's minus a squared k squared t because it's first order in t, the ddt. So the solution is the same. So multiply by the Fourier transform of this phase vector and then put it back to the inverse transform. And actually, yeah, that's the inverse transform. Yeah, inverse transform. Get it back to the solution. Right. So that is, and then you can see that when you substitute t equals 0, that is exactly the inverse transform formula for psi at t equals 0, right? That becomes size of 0. All right. How about the next one? Next one, how do you generalize from this to 3D? You see that? The same thing, right? Same corresponding thing, just make corresponding changes. So again, the square of pi becomes pi to the 3/2. And then the integration, this Cassier also becomes a vector. So this is integrating over the 3D Cassier space, and then size of 0. Now it's not. This is not the Fourier. This is the initial condition, initial psi, and then you make the corresponding change minus 2a whatever t, and then this is the vector into the minus c square, the d cubed. No, let's see. Right? Can you see that? Can you accept why this is so? Why this would be the solution for that? Can you see? Yeah, there are 3 directions. So each direction is like that, right? You can first check the initial condition when you set t equals 0. Set t equals 0, then this becomes independent of Cassier. Then this becomes, then you can pull that out of the integration. The rest is a 3-dimensional Gaussian integral. Each becomes a factor, cubic factor. Each factor gives you a square of pi, which cancels with this. So you get back to the size of 0. So that satisfies the initial condition. And then to show that, we can go through the complete square like last time, but then last time we also what we did, we ought to struggle a little bit, but eventually we showed that if we plug this back to the this equation, we show that this is exactly it satisfies this equation using this form. Just plug that back in, show that that's satisfied. You can do the same thing, like plug this back to here, and then because it depends on the vector, you can write down the dependency of the argument in three component, like the x component, you have the x minus 2a, that of t equals cx, y minus 2a, t equals cy, and then z minus 2a equals ct, square of t equals z, right? And each component, when you substitute back to here, like the DDT will operate on this one, and this one, right? And then the Laplacian such you write it like d squared dx squared plus d squared dy squared plus d squared dc squared, right? So it operates on this one, or this one. And so when you plug in back in here, you can separate the component by component. So each component satisfies exactly the 1D solution, right? Using this, you can just without actually doing the math again, that's exactly, because it's exactly the same structure as last time, right? So, so that would be the 3D generalization of the 1D formula. Is it okay? So that kind of trivial. So for diffusion equation is generalizing from 1D to 3D is much easier than the wave equation. Remember the wave equation, we did the same thing, generalized to 3D, but then it involved a more complicated Fourier transform formula. And the reason is wave equation is second order in T. Diffusion equation is just one dimension, first order in T, so it make the generalization much easier. Okay, so so that's the general formula. We could plug in that some example to look at the property of the solution, and also the property of the equation. Also, actually, before we do that, we actually can discuss a little bit of the property of the, based on the equation itself. If you look at 1D, you can say if you do an integration of the ddt integrate psi xt dx, this is just x, integrate over the whole range, right? And now the right-hand side is a square partial square psi partial x squared, right? But this is second derivative, and it's also a derivative, so you can write it down as a square partial psi partial x minus infinity, right? And you can see that from the initial condition that this boundary condition of psi that required to go to 0 at infinity, so that would be 0. That would be 0, right? And so ddt of this, now you integrate that x out, so this becomes a total derivative. ddt of this quantity is 0. Okay, it means that this is a conserved. This is a conserved quantity. Integrate this psi over the whole space is conserved. Okay, so that's one property of the diffusion equation. And likewise, you can generalize that to 3D. Now you can, if you do volume integration, and you can also just do the same argument that is also conserved in 3D. In 2D, you integrate over the 2D disk, and also it's conserved. Okay, so that's one property. Another property is that is easier to see from this formula. this or that, this in 1D or in 3D. If psi sub 0 is the initial condition, psi sub 0 is of single size, like if it's all positive, then this is initial condition, right? But then by this formula, you can see that for all time, psi is all positive, right? Because positive or 0, if size of 0 is greater than 0 or all for all x, right? That implies psi xt is all x and t, right? Can you see that, right? Because this is an integral, and then the integral has this positive factor. This exponential factor is always positive. If size of 0 is positive, then whatever you do the integration, it must be positive anytime, right? So that's a nice property because it allows you to use this equation to describe something that you expect it to be positive, like it diffuses away, but then it must still be positive, like density or temperature. It just diffuses away. Or the concentration becomes just spread out because it's not exactly diffuse. We already showed that the integration of this quantity over the whole space is conserved. So the total amount is the same. It just spread out over the whole space, right? And then, but then it keep the factor is positive. So that's a nice property that is required by physics. Okay, and likewise, if it's negative, then always negative. So, but obviously, if it is not neither this case, it can be positive or negative, then it can. Then later on, this also can be all either positive or negative, but the total amount is still conserved. Okay, so that's second property. Another property is that you find a solution, either from setting an initial condition using these two, either one of these formulas, find a solution, then there is, if phi psi sub 1 is the solution, xt. From here, from 1D, and then you can see that from the equation itself, you can see partial psi, partial t is also a solution, right? Partial psi sub 1, right? Because you can take the time derivative over the whole equation, partial psi, partial, take another time derivative, take another time derivative here, it still satisfies the same equation. So this is still a solution. And likewise, partial psi, partial x is also a solution, right? Because it's just the same, you just take the derivative over the over side, and then it still satisfies the same equation, right? So this is another way to generate different solutions. Once you get one solution based on a certain initial condition, if you like, you can find more solutions just by taking derivative and respect the t or x. And x in 3D is the same. You can take the psi y and c. All the Cartesian derivative will also satisfy that, but not the radial thing. If you write this in 3D, the radial, that would not be the case. This would not be the solution. Okay, because in 3D we write it in the Laplacian in polar coordinate, spherical coordinate. The coefficient has the radial has R dependency. So when you take the derivative over R for both sides, that will not preserve the form of the equation. So that this is not good. And then also the polar coordinate or the radial coordinate in cylindrical coordinate, that is also not good. This is also will not give you the solution. Okay, so that's another way to look at a quick way to build up a different solution. Okay, all right. So all these simple property you can see from the equation or the form of this formula, right? And then we can try some initial condition and see what we found. So this is just arbitrary formula. They like if you choose for 1D, you choose size 0, x is just a delta function x, right? And that then you can get the solution right away. And the easiest one is obviously, I mean, either one is quite easy actually, but if you use this one, so psi xt would be 1 over square of pi, and then this becomes delta function x minus 2a t e minus c square b to c, right? And then you can integrate that by using the delta function. But obviously, because the argument is not in c minus something, this you need to normalize the argument with the integration variable also. Basically, what you want to do is, I mean, there's a formula for for doing that in the other function. You can look that up, but one way to do it is just multiply the coefficient in front, multiply 2a with t. If you do that, obviously you need to divide it by the same factor, right? So once you do that, that becomes this becomes a variable, right? This becomes a variable, and then so the integration will be just the rest of the integral is wherever you see c, it becomes a c become x divided by 2a square of t, right? The only c is in here, so what you have is to write down all these coefficient first, 2a square of t, and then exponential function minus x squared divided by 4a squared t. Right. I think so, yeah. Right. So this is this will be the solution, and you can convince yourself that this is when t goes here, this actually corresponding to a delta function. I mean, this is, you probably need to normalize it a little bit. And one check is that integrate the delta function has the property of integrating delta function. This is for whole range. That must be 1, right? And then you can integrate this one psi t, psi xt, and integrate it over all x. So integrating over all x is dx. This is just double checking the algebra is correct. So 2a t, right? And then the e to the minus x squared 4 pi t and dx, right? But then you can use all these coefficient to just put it in here. Just 2a of t, right? And you see that this is just just the Gaussian, just the square of this one. The x is just basically x squared for a squared t. This square, and this becomes a Gaussian integration. A Gaussian integration gives you square root of pi, so that gives you 1. Right. So you check that this is the correct form of the generalization of a delta function when t goes to 0, because it integrates to 1, and it also satisfies what we talked about, the conserved quantity. You integrate that psi over over all space, it should be the same for all time, and that indeed obviously you check it out. Okay, so that is this property. I mean, this special solution with initial condition, delta function of the, although it's singular in the initial condition, delta function is singular, but then once t is a little bit greater than 0, then it's non-singular. It's a well-behaved function, right? Because nothing is singular for t greater than 0. And you can look at this property. Obviously, this is a Gaussian in spatial reported in space. That is a Gaussian. But then there's two properties. The one is the height of the Gaussian. The height is when x is 0. That is 1. So the height is inversely proportional to the square of t. So this height is proportional 1 over square of t. So at t goes to 0, that's obviously very, very large. At t goes to infinity, that is, you just keep decreasing in this manner, square of t. Okay, so the height decrease, and the width is given by the whatever this the denominator of the Gaussian, the square root of the denominator, right? So the width is proportional to the square of that is 2a square of t, right? So also proportional square of t. This proportional, the height proportional 1 over square of t, the width proportional to the square of t. So and that's another way to say the area will be preserved, you know, over all time. Okay, so that's give you the physical picture of a diffusion. So it start out with just a spike at infinitely large at x t at x equals 0, but the width is 0, so it's just exactly at one single point. But once it's t greater than 0, it just spread out and just keep spreading out in time. Okay, so that gives you an illustration of diffusion. Okay, so that's this special initial condition give you this qualitative picture of what the diffusion, the solution looks like in time. Okay, so that is this one. Let's keep it here because I want to tie it up with your textbook example. The textbook has an example 9.7.2. Okay, the initial condition is not like that. The initial condition in that example is a step function. The size 0 in your textbook. Let's look at that. It's from 1 to 1, minus 1 to 1, and size 0 is 1. So 1 initially. And at x is minus 1, and 1 is just drop off. So this is like a head function, or you can write it as a subtraction of the two step function. So in this case, size 0 x is. Do you know how to do it? Write that head function in using step function. So it basically, a step function is just 0 and then step up, right? Step up to 1. It's like that. So this head function is like you have a step function and step up at minus 1, go to 1 always. But in order to cut it off at 1, so you basically subtract another step function, which is 0 over here, and then go up in here. You subtract the 2, you cancel this part, right? And then this becomes 1 over here. So this is step function fade x at my x plus 1, because it will be 0 when x is less than minus 1. But because when the argument is positive, then you get 1, right? So when x is greater than minus 1, you get 1 from this one. Then you subtract. It's a function of x minus 1. Did that give you this initial condition? Is that okay? So, so that is your example in the textbook. And the solution is just like what we did. You just put it here, and then you basically using a head function, except that the head function, this x will change. So it change in time. That basically will spread out, right? It will spread out, and so that to figure out how to do it is elementary. The only thing is that when you do that, you integrate basically partially of a Gaussian function, you can say that. But it's not a total Gaussian integration because it's not integrating over all space. And what you get is what we call the error function. If you do that, except that we'll talk about error function later, which is fine. But one thing you can tie it up with what we talk about in here is that you find a solution of that. And we just talk about one property is that if this is a solution, then the derivative is also a solution. Like in this case of d psi dx is also a solution. Right? Then we can look at if the d psi dx, you can also say d psi c or dx. If you use that d psi c or dx is your initial condition, then it's also a solution. And so if you use psi c or pi as the initial condition, just you can just write down the psi c or pi. And what is the psi c or pi? Psi is given by the step function. What is psi c or pi? The derivative of the step function. What is it? Do you remember? Zero? It's not zero. It's not zero. You have a suggestion? Delta function. Yeah, exactly. Yeah. X plus 1 minus delta function. X minus 1. It's actually two delta functions, right? So each delta, each derivative of a step function is a delta function. That anyone, I mean, everyone can accept that, right? Or you remember that, or so I don't need to explain that. Okay. Okay. So once you realize that the derivative is just delta function, but we already did the delta function, so each one of them will give you a term like that. You just shift the x, right? You just shift the x, right? And that is a valid solution for the diffusion equation. And to get the solution for your textbook, obviously, this is the derivative of that. So once you get that, you can also integrate that and get the solution for that. And integration of an exponential function or minus Gaussian function will give you a error function. Okay, so that is the solution in your textbook. 9.115. It's okay. So I won't go through the integral. It's straightforward, but then we require a definition of error function we haven't gone through yet. But just to make the connection that is the two are just related to each other by a derivative or integration. Okay, so that's one special solution. That's in 1D. We can do the same thing in 3D, right? Because we have the 3D solution, right? We obviously we do a psi zero now. The x is delta function in x, and this notation means it's a three-dimensional delta function. We have a vector in the argument. So basically, this is delta x, delta y, delta z. Okay, and you can likewise plug that back into here, and then the solution will be just like what we did for 1D. And you can just copy that, except that you have different different power and pi. Pi, this is 3/2, this is 1/2, so change that to 3/2, and then this 2a square of t is coming from each integration, right? Each integration will multiply this and divided by that. So for 3D, we have three of these factors, right? So that is 1/8 of a cube, and then pi t we have, right, this factor, and the rest is just the same, because you can combine the three factor, each have the same forms, and then combine x squared plus y squared plus z squared is r squared. Okay, so you can, without doing the integration again, or I mean, it's straightforward. Anyway, you can write down the solution, and basically the form is you have this factor, which is very similar to the 1D, right? Except that we change the x to r. And then the main difference is that you have t to the 3/2 instead of t to the 1/2. The rest is just coefficient. Coefficient is because this is linear equation, so whatever the coefficient you multiply by another constant is still a solution. So that doesn't matter. Okay, so we did that, and I want to also tie it up with the textbook example 9.7.3. It talks about 3D also, but for spherically symmetric situation, which means Laplacian depends on R only, it doesn't depend on theta or phi. And but the work, the method the textbook using a kind of like a accidental relation, because if you write write out the component of the Laplacian side in the spherical symmetric case, that is in textbook 9.116. Also square u plus r square plus 2 over r u. Actually, the textbook changed notation. Let's just skip sign. Right. Okay, that's the form of Laplacian, and if it depends on R only, psi depends on R only. But then now the accidental relation is that if you define a new variable, so psi is v over R, okay? Just make a transformation instead of psi, you consider the equation for v, and you can do that by just doing the chain rule, right? So partial psi partial R is the two term. One is partial v partial R, and 1 over R, and minus v over R squared, right? That's this, and then you need another derivative, partial square psi partial R squared is you have 1 over R partial square v partial R square, and you can combine this one, the derivative over 1 over R and the derivative over v over this term, combined to be minus 2 R square plus v plus R. And then finally is the derivative over this factor, plus 2 v over R cubed. Right? And then you put everything together, basically this one plus 2 of this one divided by R, right? And you can just like multiply 2 over R here, times 2 over R square, and then add the 2, add it up, right? Add it up. This one cancel with this one, And this one cancel with this one. The all together is 1 over all. The Laplacian is the Laplacian 1 over r partial v partial r. But then the side, the TDT term, because you have this one, so 1 over r partial v partial t equals to a squared r partial square v partial r squared. You can cancel the r. So the v variable actually satisfies exactly the same as the 1D diffusion equation, just like that. So kind of accidentally, if the spherically symmetric case, it's like a 1D equation, except that you finally you need to divide it by r. Okay, and that to get the solution. Okay, so that is a nice property of the 3D situation. The same thing doesn't happen for 2D. 2D doesn't have that property. Okay, so another way to get this solution is like first we get this one, the 1D solution, but then again that if you take the derivative of this solution is still a solution. We take the derivative, you pour another x and then x over t, right? So you have an x here and then t to the 3/2 power in the denominator. But then finally you need to divide. That x becomes r in 3D. So that is there's r in here, but you divide it by r later, so cancel with this r. Finally, you get exactly the same form as this one. Okay, so the solution in your textbook using this method is exactly like what we did here. Okay, so that's almost all, except that your textbook has finally also has a discussion in cylindrical coordinate, and again it's cylindrically symmetric. That the solution does not depend on the azimuthal angle, does not depend on phi, depends on rho only. And the textbook try to do some trick in the 2D, then the Laplacian is not like that. In 2D it's rho squared, and that's a factor of 1 only. Rho. But and then finally the textbook wrote down a solution in 9.126, but then I think it's wrong. It's either a typo or I don't know whether your version has a correction. Let's just write it down. We're almost done with this is the final topic, so let's erase everything now. Your textbook wrote down 9126 of the 2D diffusion equation is right V, which is a solution. We are is proportional certain constant square of t over rho e to the minus rho square 4 a square t. That's the solution in your textbook. Do you get that? Do you have your book? Is your version like that? This is not right. This is not a solution. And first, it might be a typo. If this is V pi, then that's fine. That is coming from 9.125. You solve for V pi, and V pi will be given by something like this. And that is fine. But V pi is not the solution yet. The solution involves V, so you need to do an integration of all, and which in this case is like integration in rho. And because of this 1 over rho, that the integration will give you some kind of like exponential integral. So again, we haven't talked about those things. We probably will touch on a little bit later on when we talk about, go to the chapter about the gamma function, error function, and all that. That I think it's called E sub 1 function. So, but it's singular. But most important property is this solution is singular for all t, and unlike the solution we had even for finite t, this is singular at rho equals 0. So that it's not a good property for a solution, right? Even after you do an integration, it's still singular. So, but most importantly, your text will roll it like as a solution, because you try to say that this V is just U in 9.122 is just saying that basically this will satisfy the 2D diffusion equation with symmetrical symmetry. That's what your textbooks appear to say that. I don't know whether it's a typo or error, but one thing you can check is whether this is a solution of that. Right. So that we talk about many times. Once you get the solution of a differential equation, the ODE or PDE, the important thing is to put the solution back to the equation, because somewhere along the line you might make error, so you don't know that. And then that's the final check whether you get the correct solution. And now we can do the same thing. We can see if we can check whether this is a solution of this one. Right. Now we need all this derivative. For the time derivative, the partial v partial t, using this form. Right. So there are two t dependency, t in here, t in here. For the t in here, you get 1/2 of square of t in the denominator. Basically, is the same v, but divided by 2t, right? Because you have a 1/2 factor, and then change the square of t in the numerator to denominator, so divided by t, right? So that's the derivative over here. And the derivative over here is the same exponential function, and then you pull out minus rho squared over 4a squared t squared. Actually, plus, because when you take the derivative, this derivative over t give you minus 1 over t squared, right? You cancel negative sign plus. So basically, rho squared over 4a squared t squared times e. Right? The derivative of that when we give it this one. Okay, that's partial v partial t. And let me do partial v partial rho here. Partial v partial rho. Again, there are two dependency rho here, rho in here. But this one is minus v over rho, right? Because it's just rho to the minus 1 in here. And but this one is minus, you take a derivative, you have 2 rho, right? And then you cancel with this factor. So it's rho over 2a squared t times v. Is that okay? So that, or you can write like, I have space here, write another step. Minus 1 over rho plus rho over 2a squared t v. Okay, so that's partial v partial rho, and partial square v partial rho square is basically doing the same thing. If you take the derivative of rho v over rho, basically getting exactly the same thing. So this 1 over rho plus rho over 2a squared t squared times v. And then another is take a derivative of over this factor. And so it's plus, take the minus sign, 1 over rho squared minus this minus sign going into here, a squared t v. Okay. And what we need to know is whether this one plus 1 over rho of this one, this multiplied by 1 over rho, we can write 1 over rho plus v plus rho square. Add this two to see if it is the same as this one, right? Because now when you add that, you just write another line. Was a square v plus a rho square plus another rho v plus a rho equals to, there's lots of factor. This is 1 over rho square multiplied by the two term together and 2 1 over a square t plus rho square for a fourth t square minus 1 over plus 1 over rho square minus 1 over 2 a square t. And then this one minus 1 over rho square minus 1 over 2 a square t. Like get outside, almost outside. we get everything. Yeah, almost. All right. Now you see if we can get cancellation. Let's cancel that. And you have 1 over a square. This one. Right, this two seems like combined to this one. Hopefully I got all the algebra correct. Right, and right, and do we get something similar? Oh, we also need to multiply by a squared. Yeah. Well, we need to check whether this is this a squared. So we need to multiply a squared. Multiply a squared. You got a squared. A squared. Okay, compare this with that. Only this factor is the same, this and that. The other factor is not the same. Okay, this is 1 over 2t. This is a squared over rho squared. Not the same. This is not a solution. Okay, so sometimes it happens in textbook there. Sometimes it have error. Anyway, this is just an exercise of checking solution. All right, so that's all. But I mean, even cylindrical solution you can get from whatever we did there. Just like the 3D solution, you use a 2D, like a 2D delta function, you can also get solution of in 2D, just like 3D. That's okay. So,